In this video, we shall look at how to integrate hyperbolic functions. First, a brief introduction. Here are some definitions. Hyperbolic sine can be written in terms of exponential functions in the following manner: e to the power x minus e to the power minus x over 2. Likewise, hyperbolic cosine can be expressed as e to the power x plus e to the power minus x over 2. There are also important identities worth knowing. The first is the square of hyperbolic cosine minus the square of hyperbolic sine is 1. Another identity that proves useful is hyperbolic sine of 2x can be expressed in terms of hyperbolic sine x and hyperbolic cosine of x as follows. Namely, it is 2 times hyperbolic sine of x times hyperbolic cosine of x. Likewise, hyperbolic cosine of 2x equals the square of hyperbolic cosine of x plus the square of hyperbolic sine of x. So these identities can prove useful in integrating hyperbolic functions. Let's look at the first integral. Now we can rewrite this in terms of exponent. It is quite simply half e to the power x minus e to the power minus x dx. We know how to integrate the exponential function. So it is half. Integrating e to the power x is just e to the power x. Integrating e to the power minus x will give you minus e to the power minus x plus an integration constant c. And this is half e to the power x plus e to the power minus x plus an integration constant c. And the first term is just the hyperbolic cosine of x and plus integration constant, and that's the final answer. Now this integral, we can do the same technique to solve this integral. Definition of hyperbolic cosine of x in terms of exponential function is half e to the power x plus e to the power minus x dx. So integrating e to the power x will give you e to the power x. Integrating e to the power minus x will give you minus e to the power minus x plus an integration constant, let's call it d. And this is just a hyperbolic sine of x plus integration constant d. And that's the full answer. What about this integral? Let's rewrite that in terms of hyperbolic sine and hyperbolic cosine. Hyperbolic tangent is hyperbolic sine of x over hyperbolic cosine of x dx. Now we can set hyperbolic cosine of x to be u. So the differential of u is just hyperbolic sine of x dx. So this is what appears in the numerator. So your integral will simply become du over u, which is natural log of u. Putting in the expression for u, which is hyperbolic cosine of x, you get natural log hyperbolic cosine of x plus an integration constant, let's say c. And that's the final answer. What about this integral of hyperbolic cotangent of x? Again, cotangent of x is hyperbolic cosine of x over hyperbolic sine of x dx. So in this case, we can use similar substitution. Now let's substitute u to be the hyperbolic sine of x. So du is hyperbolic cosine of x dx. So let's put all this inside there, and you get an integral in terms of u in the following manner. And this is again natural log of u, putting back the expression for u, which in this case is hyperbolic sine of x. You get natural log hyperbolic sine of x plus an integration constant, let's call it e. And that's the final answer. What about this one? Hyperbolic secant of x is 1 over hyperbolic cosine of x. And then you have the dx. We know hyperbolic cosine of x is e to the power x plus e to the power minus x over 2. Let's substitute this definition inside the integrand. And the above integral will become 2 dx over e to the power x plus e to the power minus x. So let's substitute e to the power x as, for example, v. Then differential of v is e to the power x dx. Now let's go back to the original integral and multiply up and down by e to the power x, like that. We are not changing anything because this is essentially 1. So you have an integral of 2 e to the power x dx in the numerator. The denominator becomes e to the power x times e to the power x is e to the power 2x. E to the power x times e to the power minus x is just 1. So let's rewrite this integral in terms of v. You can take 2 out, it's a constant. Ex dx is just differential of v, dv. E to the power 2x is v squared plus 1. From our previous video, we know the integral of 1 over v squared plus 1 with respect to v is just the inverse of tangential function, v, plus an integration constant, let's call it c. Substituting back the expression for v, you get 2 inverse of tangent e to the power x plus that integration constant. And that's the final answer. What about this one? Now we know that hyperbolic cosecant of x is 1 over hyperbolic sine of x. And that is just 2 over e to the power x minus e to the power minus x. So substituting this expression in here, we get an integral of 2 dx over e to the power x minus e to the power minus x. Again, using the technique of multiplying up and down by 1 in the form of e to the power x over e to the power x, you can take the 2 out. The numerator becomes e to the power x dx. The denominator becomes e to the power 2x minus 1. So let's make the following substitution. V is e to the power x, so dv is e to the power x dx. And in terms of a v, that integral becomes the integral dv over v squared minus 1. If we remember, the method of partial fractions will yield the following result. 2 over v squared minus 1 is 1 over v minus 1 minus 1 over v plus 1. So we can substitute this result in the integrand. So this integral can be broken up into 2. The first one is dv over v minus 1 minus dv over v plus 1. The first integral will give you natural log of v minus 1. The second integral is natural log of v plus 1 plus an integration constant, let's call it g. Combining the two natural logs, we get natural log of v minus 1 over v plus 1 plus the integration constant g. Let's rewrite this integral in terms of x, so that is just natural log of e to the power x minus 1 over e to the power x plus 1 plus integration constant g. Now let's take a look at the argument of that natural log. E to the power x minus 1 over e to the power x plus 1. Let's multiply this term with e to the power minus x over 2 over e to the power minus x over 2. And what you'll get is natural log of e to the power x over 2 minus e to the power minus x over 2 over e to the power x over 2 plus e to the power minus x over 2 plus the integration constant. And we note that this is just natural log of hyperbolic sine of x over 2 over hyperbolic cosine of x over 2 plus the integration constant, which will give you the following answer. Natural log of hyperbolic tangent of x over 2 plus the integration constant g, and that's the final answer. What about this following integral? Let's go back and look at the important identity that we discussed earlier, namely hyperbolic cosine squared x minus hyperbolic sine square x equals to 1, and the other one is hyperbolic cosine square x plus hyperbolic sine square x equals to hyperbolic cosine of 2x. You see, when you take this equation, you minus that equation, you will get 2 hyperbolic sine square x equals hyperbolic cosine of 2x minus 1. So this identity enables us to write that integral in a following manner. Half integral of hyperbolic cosine of 2x minus 1 dx, which is pretty easy. You can write the half in front. Integrating hyperbolic cosine of 2x will give you half hyperbolic sine of 2x. Now integrating 1, you simply get x plus an integration constant c. Now we can simplify it a little bit further. We know that hyperbolic sine of 2x is 2 hyperbolic cosine of x and hyperbolic sine of x. So the above answer can be written as half times hyperbolic cosine of x times hyperbolic sine of x minus x plus the integration constant c. Now just to note, I have used the following abbreviation, CH to denote hyperbolic cosine and SH to denote the hyperbolic sine. Finally, let's look at the following integral. We can rewrite this as hyperbolic tangent of x times hyperbolic tangent square x dx. We know that hyperbolic cosine squared x minus hyperbolic sine squared x equals to 1. So that means dividing this identity by the square of hyperbolic cosine of x, you will get 1 minus the square of hyperbolic tangent of x equals the square of hyperbolic secant of x. And we can use this identity to rewrite the integrand, hyperbolic tangent of x times 1 minus the square of hyperbolic secant of x dx. So what do you have? You have two integrals. The first integral is hyperbolic tangent of x dx minus the second integral is hyperbolic tangent of x times the square of hyperbolic secant of x dx. This integral has been discussed. The answer is natural log of hyperbolic cosine of x. So let's concentrate on the second integral, which we call I. Let's see how to solve I. Let's denote u to be hyperbolic tangent of x. So du is the square of hyperbolic secant of x dx. So I will simply becomes u du, which is half u squared, essentially. Substituting the expression for u, you get half square of hyperbolic tangent x. So the final answer to the original integral is this expression minus that plus an integration constant, which is natural log of hyperbolic cosine of x minus half the square of hyperbolic tangent of x plus an integration constant, let's call it d, and that solves the problem. As always, thank you for watching.